We're talking about improper integrals. These will be on the homework next week. Improper integrals. All right. These are, like the classic example, something like this. I don't think we need to go through this whole example, but it's improper when you're integrating like up to infinity. All right. And the way to do this, how to make sense of integrating up to infinity, you always begin, before doing anything else, by turning this into a limit. So what does it mean to integrate up to infinity? It means really you just integrate up to some point and then figure out what the integral is, and then you take the limit as that point goes up to infinity. That's how you actually calculate these. This is a fairly simple example that we did last time. I don't think we need to go through that example again, but this is the idea. All right. Now, there are two ways that these can be a little more interesting than the ones that we talked about last time. One way is just that some of these integrals require our classic tricks. So I'm going to just do a couple of the type. So this is an improper, but none of the ones we did last time are like this, because this one, in order to do the integral, you have to do one of our integration tricks. Anybody got a suggestion? What's the proper way to do this integral? Yeah?
Integration by parts.
I would say your choices are parts, U substitution, trig substitution. It's not that. I didn't like what he said before. Anyone have another idea? I think we should do a U substitution. It's because the x squared up top, it messes it up if you try to do parts. This becomes too complicated to do using parts. But this is a good choice for the U substitution, because I have this like extra x down here, but that x is something like the derivative of what's on the inside. So I'm going to do the U substitution. You can try parts, but it's not a good choice for this example. All right, so let's try the U substitution. We, as usual, let the U be the thing on the inside, and in this case, I'm referring to the inside of the exponent. So U is minus x squared, and then the du is minus 2x dx. All right. Actually, I should have, even before really thinking about that, changed this to a lim, 0 to t. X e to the minus x squared dx. All right. Now I find it easier to not change the boundary values. I know some people, when you do U substitution, like to change the boundaries right up front, and actually that's what I did on that test question we just tried. But it's a little bit of a pain because the boundary values are not even specific numbers. You have this t up there. I'm just going to leave the values until the very end after I do the substitution. So this, when we do the substitution, becomes integral of e to the u, and then that x and dx, if we divide the constant over here. This is a straightforward U substitution. This is e to the u inside the integral, and also x times dx, but x times dx right here is negative a half du. So this is e to the u times negative a half du. And there are boundary values of 0 and t, but those are boundary values for x, so I'm not going to write I don't want to bother finding the corresponding boundary values for you. Now, how to do this integral? I would pull the constant all the way out, and in fact, you can actually pull a constant through a lim also. So this can really go all the way out front. And it is just integral e to the u du. And what is the integral e to the u du? It is e to the u, yeah. The integral of e to the u is e to the u. So this is e to the u. And I'm going to replace my original variable e to the minus x squared. And now we're plugging in 0 and t. Remember, you have to put the original variable back in before you try to plug the values. Right? Plug them in. I put t, and subtract, and I put 0. So minus a half lim t goes to infinity. And now it's going to be e to the minus t squared minus e to the 0. Minus 0 squared. All right. And now we have to do this lim. Usually when you do the lim, the answer is either like 0 or does not exist or something like that. Anybody want to say I mean, of course, I don't care about this when it comes to doing the limit. This e to the 0 equals 1. So this is just going to be a 1 as part of my answer. What about this part? Is that 0 or is it infinity or is it something else? Any ideas? Yeah?
0.
It's 0. Why do you say 0? It's true.
It's 1 over e to the power of 0.
Yeah, right. When you see a negative exponent here, I would like to write that as a denominator. Then that is clearer to me that it's going to be 0. This is 1 over e to the t squared minus 1, right? And now I can see when t becomes infinite, this fraction here, its denominator becomes infinite. And so that's a 0. So that's like a 1 over infinity, which is a 0. So my final answer is minus a half, 0, minus 1. I guess just a half is the answer. All right. So this is a improper integral where you got to do the u substitution. But, it's fine. It all works out exactly the same way. All right. Sometimes you have to do parts. Can we try one like that? Again, there's not really any big surprise. Although something a little interesting will happen at the end of this one. But let's try this one. Is very similar, but it doesn't have the squared inside of the exponent. This one actually you cannot do with the substitution. You instead must do with the parts. And it can be tricky sometimes to decide which of your tricks you want to use. But anyway, before any of that, I'm going to turn this into a lim. T goes to infinity, 0 to t, x e to the minus x. All right, and now we're going to do parts. The u, what should I choose for the u here? Any parts stands out there? X, yeah. He's a part stand. Right, I have like a polynomial part and exponential part. I choose the polynomial part to be the u. So then the du is dx, and then the dv is e to the negative x. The v would be the integral of that, the antiderivative of that, which would be minus e to the minus x. All right. And we do it. So we go lim, t goes to infinity. And it is the parts formula, I hope everyone remembers, uv minus integral v du. So that's u is x, v is minus e to the minus x, minus integral v du. V is minus e to the minus x, and du is dx. All right? That's my parts. We can, I suppose, simplify ever so slightly. I have that minus minus. Those can just become pluses. And then we do the inner integral again. Integral of e to the minus x is again minus e to the minus x. So this is going to be lim, t goes to infinity, x times e to the minus x. Can I just put the minus up there? And then minus e to the minus x, like so. And since this is a definite integral, that's the parts. Remember, if we have boundary values to plug in, we do the whole parts thing and then plug the values in at the very end to everything. So the t and the 0 get plugged into x everywhere you see it. All right, so this is lim t goes to infinity. I'm plugging in the t. Minus t e to the negative t minus e to the negative t. And then subtract, plugging in 0. Minus 0 e to the negative 0 minus e to the negative 0. And we have to do this limit now. Towards the end of finding the limit, as usual, I like to write, if I see negative exponents and I'm trying to find the limit, I like to write that as a denominator, right? So those e to the minus t's, I'm going to write them as e to the t in the denominator. I just have an easier time thinking about the limbs that way. So this is t over e to the t, right? And then the next one is just a 1 over e to the t. And then this stuff at the end is whatever it is. Those are just numbers. And I guess it's minus 0 minus 1, right? And we now have to do those limits. There's really two limits to consider, this one and this one, right? what happens when I plug t going to infinity. I think the second one is a little clearer. Right here, when I plug in infinity, if you imagine plugging in infinity, it basically looks like a 1 over infinity, which is 0. So that second part is going to be 0. Maybe I'll just as a little, just because this is slightly complicated, as a little sidebar here, the second limit, 1 over e to the t, is 0. All right, because what I just said, this is basically like 1 over infinity. What about this one? Lim t goes to infinity, t over e to the t. That's the other one that I care about. This one, if I were to plug in the infinity, so to speak, what happens? Yeah?
Infinity over infinity.
You get infinity over infinity, and what's a fella to do in such a case? Yeah? Yeah, you do the L'Hopital's rule in that case, if you get infinity over infinity. So this can happen at the end of an improper integral. Often you have to use L'Hopital's rule in order to figure out what the limit is. So this is an indeterminate form, which means I'm going to use the L'Hopital rule. L hop. So this becomes lim t goes to infinity. This is the L'Hopital step. I'm taking the derivative on the top and the bottom. We get 1 up top and e to the t on the bottom. And now when you plug in, you get 1 over infinity, which is 0. All right. So that means the first limit overall, so this limit we said was 0. And this limit also is 0. Although that first one, it ended up being 0 also, but it was for slightly more complicated reasons because of the L'Hopital's rule. All right. So what's my final answer? I think those first two parts are 0. So this is the whole answer, and it's just 1, right? So my final answer is 1. Because everything else is 0. All right. Improper integrals. Sometimes you need the L'Hopital at the end. That's what I'm saying. Any questions about that one? All right. I said I was going to talk about 2 sort of variations on the improper integrals. This was the first. Just like sometimes when you do the improper integral, you have to use some of your fancier integration tricks. The second variation is actually, in my opinion, more interesting and a little more, a little sneakier. There are sneaky ones, I will call them. Sometimes there are sneaky ones of improper integrals. What I mean by sneaky ones is something like this. That is an improper integral, even though you don't see infinity, all right? What I've been saying all along is like, what improper integral means is there's an infinity as one of the boundary values. But actually, this is also improper. I say sneaky ones because if you're not really paying attention, you might not even realize that this is improper. This is also improper. Can anybody say why? Yeah?
Because when you plug in 0, it's undefined.
Yeah, because 0 is not actually, like this function here is not continuous at 0. Like if you think about what the endpoints look like, it's a little weird that you can't even do that endpoint. In fact, if you were to look at a graph of this, it would look like 1 over x cubed basically looks the same as 1 over x. It looks like that, right? And what I'm talking about here is the area from 0 up to 4. And again, it's improper because this is an area which stretches on forever. It's just, it goes up this time rather than out to one or the other side. So I will say it's improper since one of the endpoints is a vertical asymptote, a vert-tote, as I say, a vertical asymptote. All right, that means it's actually just like the other, like the area that we're talking about is just like those other ones that we were talking about, going out to infinity. It's just that it's like it's not going to infinity in the x direction, but it is in the y direction. So we need to treat this in the same way. It is a vertical asymptote. I like to write tote. I know it sounds stupid. Some people abbreviate the word asymptote by writing ASS period, and they chuckle to themselves. There's only one S in the word asymptote. Yeah. I once saw someone on their homework write vert ass, which I thought sounded like it should mean something. When I was a kid, they weren't into that, but now, what's the thing? I don't know. It doesn't mean something, does it? Only in my imagination. So anyway, we got to do this as an improper integral. So since this is improper, since one point is a vertical asymptote, how do we handle it? We do a limit. It's just this time, it has to be like this. Lim t goes to 0, t to 4. All right, so the boundary value, which is kind of like acting like infinity here, is the 0. The 4 is no problem. It's the 0 that gives us the problem. And our strategy is exactly like the other improper integrals. You turn it into a limit as t approaches sort of the problem value, be it infinity or something where there's an asymptote. All right, but anyway, this like you can do in exactly the same way. So let's just try this one. How would I do that integral? 1 over x cubed? What do you think? Yeah? Yeah, you think of this as x to the minus 3, first of all. And then you just do the usual, power thing. So lim t goes to 0. Yeah, he said minus a half x to the minus 2, right? And then we plug the values, 4 and t, and then take the lim as t goes to 0. So this is minus a half. Sorry, I should write lim again. Plug the values. So minus a half times 4 to the negative 2. That's just a number, whatever that is. And then the other one, minus negative a half times t to the negative 2. And we have to do the limit as t goes to 0. Again, I see negative exponent on that t. It's clearer to me to write it as a fraction. So this number at the beginning I don't really care about. It is whatever that number is. But here it's really a plus, I guess, well, I'll put a half out here and then 1 over t squared. And we're trying to plug in t going to 0. What are you going to get? We get a number from that. This first thing is just a number. What about this? When it comes to these limits, usually you're either going to say it's all 0 or it does not exist. What do you think? Does not exist. Why do you say that?
It's 1 over 0.
Yeah, because you're plugging t going to 0, and this is going to look like 1 over 0, and so the limit does not exist. So this, if you like this part right here becomes 1 over 0, and so the limit does not exist. All right? Or the language that we usually use in this context is we say the integral diverges. Yeah?
Could you just do the limit as x approaches 0 from the right or the left so it would exist? So that we get a convergent integral?
It would not converge. So actually this is a good point, and this is something that I meant to mention. If you see the examples in the book when they do this, actually they would write it instead, and this is not wrong, they would write it instead as limit t goes to 0 from the right. And the reason, that's like slightly more specific than what I wrote, but the reason why it's from the right is because they have this picture in mind. Actually, it doesn't matter if the value was approaching from the left. All that we care about is if t is approaching 0 from the right. And so if you look up examples in the book, they might say from the right, approaching from the right. But in this example, even so, if you approach from the right, you're still going to get a 1 over 0 here. So you could say that this integral equals infinity if you like, although even so it doesn't converge. Like equaling infinity is still diverging. It is, I suppose, slightly more accurate or more specific to write it as a one-sided limit, but not really necessary in this case. Right? It doesn't change the answer. All right.
Wouldn't it give you like value then? Because it would be 0.
It'd be 1 over 0 still.
If it approached from the right, wouldn't it be 1 over infinity?
No, it'd be like the value that t is getting close to is 0, not infinity.
Oh.
Yeah. it'd be like 1 over 0, which 1 over 0 itself is like positive infinity in this case. Yeah, but it diverges either way. Yeah, this is a good thing to think about. I got one for you all to try. How about this right here? You'll have to decide for yourself which of those two values is the one that needs to be turned into a limit, although not so difficult in this case. But.
What you wrote is correct for 3 root. How's it going? So this is going to be 2 thirds. It would be 3 over 2. It'd be 3 left. Yeah. All right. Okay. That's looking good. What's the limit going to do? You should just, since it's t going to 0, that means you should just set that into 0.
No, because you have to do the x first. You can't just tell that to the positive.
No, but this is the same amount of square root of something.
Because the negative 3 is like underneath your back.
You'll get the same answer.
Are you?
Because I did like a negative times the, like a
Yeah, you
minus
can't do
times
that.
that.
This minus can't do it. It sounds like you're like pulling this in. But that's not the key. Yeah, that plus that is actually minus.
Because this is this. There's an even approximation on this.
Going to zero, so you can just do this.
All right, I'm going to say what I got here. Most people settled down and decided to write the integral this way. X to the negative 1/3. The cube root of x is 1/3 power, and it's in the denominator, so it's a negative 1/3. And the zero value is the one that's a real issue in this problem, and so you need to turn the zero into a t. All right, and now the rest of it is kind of straightforward as long as you keep your wits about you. The integral of x to the minus a third, you add 1 in the exponent, it becomes 2/3, and then I will get 3 halves x to the 2/3. Right? And then I'm going to plug in t and negative 3. So lim t goes to 0. 3 halves times t to the 2/3 minus 3 halves times negative 3 to the 2/3. And it's a lim t going to 0. This is actually, to me, easier than thinking about lim t going to infinity. You just plug 0 in for t here and see what happens. You get 3 halves times 0 to the 2/3. That's 0, and then this is a number, and that's going to be the answer. 3 halves minus 3 to the 2/3. That's 0 at the beginning. So my final answer is minus 3 halves, negative 3 to the 2/3. All right? You can type this in your calculator if you want to. 2/3 power means you square it and then do the cube root, so you could also write this as 9, the cube root of 9, which wouldn't simplify any more than that. All right? Great. That's the sneaky ones. Now, this was a sneaky one, I guess. I mean, you knew it was coming, but the moral of the story is sometimes it doesn't look like an improper integral, but you will realize that it's an improper integral upon closer examination. It can be a little worse than that. So this is sort of super sneaky, something like this. Ultra sneaky. All right, what is so sneaky about this one? This one actually, even if you are concerned about one of the endpoints being an asymptote, actually neither of the endpoints is an asymptote here, but there's still an issue. You got an issue?
Natural log of a negative number.
You can't take the natural log of a negative number. This is true, but these sound like the words of an absolute value hater. Because when I do the antiderivative of this is ln absolute value x, and then when I plug in the -1 here, it's fine. Yeah. So that actually is not the issue. There is still an issue with this. No offense, calling you a hater. I know many absolute value haters.
ln x's graph doesn't have like -1 and 3 connecting on its graph. -1 is on the other side of the like asymptote thing.
Yeah. I think the issue is 1 over x has an asymptote. It's not, the asymptote is not at -1 or at 3, but it's in between them. So if you think about what does the picture of this area look like? It is this, and the area I'm talking about is from here to here, right? It's still one of these weird, it's actually like even worse than before, right? The asymptote is in the middle. This means we need to work quite a bit harder. So this one here, this is improper since we are integrating across an asymptote, right? And that across a vert-ass, as they say, a vertical asymptote. All right, we're integrating across a vertical asymptote, and that means the areas we're talking about, at least in principle, they could be infinite, and so we have to treat this like an improper integral. And this one I say is extra sneaky because this one you could, if you're not thinking about this, your sort of stupid little brother who never thinks about anything would be tempted to say this is just ln absolute value x plugging in 3 and negative 1, ln of 3 minus ln of 1. This looks like you get an actual answer, but that's wrong. So this, if you are not aware of the asymptote in the middle, you might feel like you just do the integral and everything worked out fine, but it didn't work out fine. This is actually not the correct answer. So you have to, it means really, from now on for the rest of your life, every time you do an integral, you have to check to make sure there's no asymptote inside the range of values. And this is a serious thing that can happen often when you're doing integrals. So you must verify that there are no asymptotes on the inside. What if there are asymptotes on the inside? How do we handle this when it's like on both sides we have two separate areas? We must, so to do it properly, we split the integral at x equals 0. In this case, we split it at x equals 0 because that's where the vertical asymptote is. So in general, we split it at the asymptote. Split the integral. So what I mean by split the integral is I'm going to write minus 1 to 3, 1 over x dx is the integral minus 1 to 0, 1 over x dx, plus the integral 0 to 3, 1 over x dx. And then each of those is an improper. And we do them separately, and then we add the answers together. This is a real pain to do, and these can take you a while to work out, but this is what we have to do. So each of these are now two different impropers. All right. And let me just say at this point, if either diverges, then we say the whole thing diverges. So when you calculate each one of these separately, it might be that you get like 2 is the answer for the first one, but then the second one diverges. 2 plus diverges, you just say diverges, right? But if you actually get a real number for both of them, you would add those two numbers together, and that's the answer. All right. So let's actually try these. I mean, this, as far as these problems go, these are not terribly difficult ones. So let's do this one first. Integral minus 1 to 0, 1 over x. So the sort of problem value is the 0. That's where the asymptote is. So I turn this into a limit. X going to 0, not x. T going to 0. Integral minus 1 to t, 1 over x dx. The integral 1 over x is ln absolute value x. So this becomes lim t goes to 0, ln absolute value x, plugging in minus 1 and t. Plug those in. Absolute value t minus ln absolute value negative 1. Absolute value negative 1 is 1. Ln of 1 is 1. So, ln of 1 is 0. So that second part actually equals 0. What about the first part, though? And here we have to think a little bit about what happens to ln of t when t approaches 0. This, perhaps you should maybe remember what the graph of the ln looks like. Yeah? It looks like negative infinity. Yeah, the graph of the natural log, surely you remember, looks like that, right? And so as t approaches 0 here, that value becomes negative infinity. So this goes to minus infinity. So this one actually diverges. Come on now. This half of the integral diverges. But remember what I said up there. If either one diverges, then we say the whole thing diverges. So if I wanted to just say my answer clearly, this integral diverges. Because I broke it into two pieces, and one of those pieces diverged. So we say the whole thing diverges. All right. That's how we do one of these. All right, I thought we should probably do one example where it doesn't diverge. So let's try one, and then I have one for you to try. I don't know if we'll get that far, but let's try another one. Integral 0 to 5, 1 over cube root x minus 2. I'm into those cube roots today, I guess. All right. Now, if you see this on our quiz, this will be labeled as the improper integrals problem, so you will be wise to the sneakiness. But you'll have to decide where is the asymptote in this case. Is it at the 0 or at the 5 or somewhere in between? Yeah. It's at x equals 2. Yeah. So I hope that everybody remembers how to look at this function here and decide for yourself where are the discontinuities of this function. It's basically going to happen when the denominator is 0, and that would be x equals 2. So this one has a vertical asymptote at x equals 2. So we're going to split the integral at x equals 2. So I write the original one splitting at x equals 2. So I'm going to go 0 to 2. And then 2 to 5. Integral 2 to 5. And we're going to do each of those separately. This is kind of a lot of work to do each of them separately, although it's the same integral both times. So really the only difference is the values you plug in. So it's not so bad, but it is a pain. So let's do the first one. Integral 0 to 2. 1 over, could I write this again as a minus 1/3 power, right? That's what that is. Dividing by the cube root is a minus 1/3 power. And the problem value here is the 2, so I'm going to turn this into lim t goes to 2, integral 0 to t, x minus 2 to the negative 1/3. Any suggestions on how we can do this integral? It's a little weird with the parentheses and all. Yes. Let's do the u substitution. What do you want for the u?
X minus 2.
Yeah, the inside of the parentheses. This is a fairly simple u substitution. Maybe it will seem too simple, but the u is x minus 2. The du is just dx. So that is just going to say u to the negative 1/3. U to the minus 1/3 du, right? Do the integral, it becomes, actually just like the one we just did, a 3/2 u to the 2/3, right? Still with the lim out front. T goes to 2, 3/2 u to the 2/3, and then we need to plug the values in. I will first replace the original variable of x. So this says lim t goes to 2, 3/2, instead of u, it's x minus 2, 2/3, and then we're going to plug in 0 and t. Those are the values of x. All right, plug them in. So we get t lim x goes to 2, not x, t. Lim t goes to 2. 3/2 t minus 2 to the 2/3 minus 3/2 t minus, 0 minus 2. That's just minus 2 to the 2/3. And then we're going to plug in t equals 2. This out here is just a number, this part back here. Right here, when I plug t equals 2, it's just going to say 0 to the 2/3, which is 0. So the limit does exist. And it's just equal to, well, I'll write it in. 2 minus 2, right? That's what you get when you plug in 2. And then minus 3/2 negative 2 to the 2/3. This is 0, so my final answer, well, for this half at least, is negative 3/2. Negative 2 to the 2/3. All right. So that's the value of the first of these two things. We split it into two parts. That's the first part, the area on the left of the asymptote. All right, and it converges. Okay, let's try the other one. The other one is almost exactly the same. So actually, I'm not going to work through all the steps, but let's just try to say what it would look like. So the other one, remember, is from 2 up to 5. Integral from 2 to 5, and the same thing. It's x minus 2 to the minus 1/3 dx. This one I turn into a limit. It's lim t goes to 2, integral t to 5. X minus 2 to the minus 1/3 dx. All right. I would like to skip a bunch of steps from above. It's the same thing inside of the integral. So when we do we're going to do the same u substitution, the same antiderivative. What can I skip to? I think really it's sort of from here all the way down to here will be exactly the same. So this integral is the same as that, only instead of 0 to t, it'll be t to 5. All right? It's all the same steps there. And if you're doing this on a homework or on the quiz or something, I would expect you to, you can work it all out if you want, but I would expect you to skip those steps. It is lim t goes to 2, integral, same thing, but, not integral. I'm doing the antiderivative. 3/2 x minus 2 to the 2/3. The difference is the values. Instead of like that green underlined thing, instead of 0 and t, it's now t and 5. Like that. And then, we plug them in and take the lim. So 3/2, 5 minus 2 to the 2/3. That is just some real number. And then 3/2 t minus 2 to the 2/3. And what happens when t goes to 2? This becomes a 2 minus 2, so that becomes 0. And the answer is just whatever that first thing is. All right. In the limit, the second term becomes 0 because it's going to say 2 minus 2. So that is the whole answer. 3/2, I guess that's 3 inside the parentheses. All right. The work is done. We should say the final answer then. So the whole thing, integral from it was from 0 to 5 of this business. This is what we started with, is the sum of those two answers. So there was this one and this one, right? Those two things we are adding together. One of them is negative. Negative 3/2 minus 2 to the 2/3, and then plus 3/2 times 3 to the 2/3. That is just some number. All right. So it can be sometimes when you integrate through an asymptote like this, you really do still get a real answer. Thoughts about that one? All right, great. I got one for you all to try. I think we can try this. We may not. We got 7 minutes remaining. This is really the end of the improper integral stuff, so I just want to do one last example, and then we can start a new topic next time. See what you think about that. You'll have to decide for yourself, first of all, where is the asymptote, and then break the integral at that point, and then see what happens to the rest of it. You want to talk about this one? I know not everybody finished, but we've got to go in a moment. First of all, everybody said the vertical asymptote here is at x equal 4, so that's where we have to split the integral apart. So I'm going to go 1 to 4 and then also 4 to 10. And let's just start with the 1 to 4 one. Turn it into this limit, t going to 4, because that's the 4 is where the asymptote is. And now to do this integral, you have to do this sort of baby u substitution again. U equals x minus 4. The du is just dx. And so this becomes lim t goes to 4 integral u to the negative 2 du. Do the integral, I get minus u to the minus 1. Replacing the original variable gives me minus x minus 4 to the minus 1, plugging in 1 to t, right? I hope I'm doing all right so far. And now this, with a minus 1 power, well, plug in the t's. Maybe I'll write that as a fraction also, just because I'm that guy. Minus 1 over x minus 4, right? That's what that is, plugging in 1 and t. So I get minus 1 over t minus 4 minus 1 over 1 minus 4. And what do we get when we take the limit? The first fraction there gives you a 1 over 0. And so that means this whole thing diverges. This right here gives me 1 over 0. So this half diverges, which means the entire thing diverges. All right. See you all tomorrow. Let me know if you want to try again one of them old ones. I would be happy to do it.